All right, let's just get right into it. Welcome to this explainer on Quantum Computing 101. Look, if you're an AI developer, a cybersecurity expert, or an infrastructure leader trying to figure out what's an actual technological breakthrough and what's just, well, science fiction, you are in exactly the right place. Today, we're taking a strictly hyper-resistant look into quantum computing. We're going to break down the practical truths, figure out what this technology actually is, and honestly, just as importantly, what it isn't. So get ready for a highly focused look at the very future of computation. Here's our roadmap for today. We're going to start by looking beyond the quantum hype, then examine the fundamental difference between bits and qubits. After that, we'll unpack the 4 core behaviors of quantum systems, map out where this actually matters, give ourselves a reality check on current hardware, and finally, talk about how to prep for imminent quantum cybersecurity threats. All right, part 1, Beyond the Quantum Hype. To really grasp why quantum matters, we have to recognize that it expands the very model of computation itself. You've probably seen pictures of those intricate, freezing cold golden structures, often called quantum chandeliers. They look completely sci-fi, and because of that, people make a lot of really lazy analogies. Let's just reject those right out of the gate. A quantum computer is not a faster laptop, it is not a replacement for your GPUs, and it is absolutely not some magic machine that tries every possible answer at the exact same time. It's actually a highly specialized computational model that uses quantum mechanical behavior to solve very specific classes of problems in a fundamentally different way. The reason we even need this tech in the first place was perfectly captured by the legendary physicist Richard Feynman. He pointed out that nature itself isn't classical, right? It's quantum mechanical. So some problems are incredibly hard for our current computers, like simulating complex chemistry or materials, precisely because the thing we are trying to model is quantum. If you want to simulate nature exactly, you need a computer that actually plays by nature's rules. That's the real driving force here. Moving on to part 2, bits versus qubits. Let's see how this paradigm shift actually plays out in the hardware. The primary distinction here isn't just raw speed, it's representation. We all know the classical bit, right? It's a 0 or a 1. It's the highly stable, definite value powering every ordinary digital system we use today. But a qubit? A qubit exists in a fluid quantum state that we manipulate entirely before measurement. And here's a huge mistake to avoid. You're going to hear this one a lot. People think a qubit just magically gives you both answers for free. It doesn't. Its true power comes from how we shape probabilities before we measure it and force it to pick a classical outcome. Which brings us to part 3, the 4 core behaviors. I want to slow down a little bit here, because these next 4 terms, they aren't marketing buzzwords. They define the literal operating model of quantum computing. First up is superposition. This just means a quantum state can encode combinations of possibilities before it gets measured. Think of it like setting the stage. By placing qubits into superposition, we create this incredibly rich, complex mathematical landscape that lets our quantum gates start doing their highly specialized work. Next is interference. And honestly, this is where the real magic happens. Quantum operations use interference to amplify useful outcomes and suppress the less useful ones. Think about Grover's algorithm conceptually. Quantum speedup doesn't come from instantly inspecting every answer, it comes from probability amplification. It's kind of like noise-canceling headphones, but for computation. You're actively canceling out the wrong answers so the correct answer peaks. The third behavior is entanglement. This is when qubits share relationships that simply cannot be described by looking at each qubit independently. It's this fundamental, almost eerie link that allows highly complex systems to be modeled together. Change the state of one entangled qubit, and it instantly relates to the state of the other, no matter how complex the system gets. And finally, we have measurement. Reading the system collapses all that rich, delicate quantum complexity into standard classical info, a 0 or a 1. And doing so actually changes what can be known about the system afterward. So a truly successful quantum algorithm takes all of these behaviors, superposition, interference, entanglement, and organizes them into a precise circuit that makes your desired answer the absolute most likely outcome when you finally take that measurement. All right, part 4, where it actually matters. Let's pivot from theory to pragmatic reality. We need to focus on specialized problem classes, not just wild vendor promises. These are the domains where quantum is positioned to be a massive accelerator. First, quantum simulation. Modeling molecules, discovering new battery materials, drug discovery, perfectly mimicking quantum chemistry. Next, optimization and sampling. Think insanely complex routing, scheduling, and massive supply chain logistics. Third is cryptography, which we'll dive into heavily in a second because of the public key risks. And finally, scientific AI. Interestingly, while the media loves talking about quantum for AI, the near-term practical reality is actually AI for quantum, using classical AI to help clean up noise and calibrate early quantum computers so they actually work better.
So let's do part 5, the NISQ reality check.
NISQ stands for Noisy Intermediate Scale Quantum. It's the era of hardware we're living in right now. Current systems are amazing research platforms, for sure, but they are incredibly noisy, they're limited, and they require highly difficult error correction. It's a really long road from the lab to the enterprise. Think back to Google's famous 2019 Sycamore experiment. They hit a huge scientific milestone, Step 1, quantum advantage. But the task they did? It wasn't a general business application. To actually reach Step 4, real business value, you have to pass through Step 2, integrating it into a useful workflow, and Step 3, actually ensuring reliable operations with proper governance and low error rates. Just because a scientific milestone makes the news doesn't mean it's a deployable enterprise solution today.
Which leads us to part 6, preparing for quantum threats. Now, even if a perfectly error-corrected quantum computer is years away, the cybersecurity risk starts literally right now. The crucial concept here is the harvest now, decrypt later timeline. Adversaries can capture your encrypted data today over public networks, right? And they just sit on it, they store it until a quantum computer is finally capable of breaking the encryption, and they decrypt it later. So if your organization holds long-lived data, trade secrets, national security info, health records, where the confidentiality needs to outlast the time it'll take you to upgrade your cryptography, you are already exposed to debt. That means you have to take actionable defense steps immediately. We call these post-quantum cryptography, or PQC readiness actions. First, inventory your current cryptography. Find out where your long-lived data actually lives. You've got to plan for crypto agility, the ability to swap out encryption methods quickly without breaking your entire tech stack. And absolutely crucial, track and test the finalized 2024 NIST post-quantum cryptography standards. Those algorithms, MLChem, MLDSA, and SLHDSA, are the newly minted tools specifically designed to protect your classical computers against these future quantum attacks. So let's wrap this whole thing up. The core takeaway from everything we've talked about today is this. Disciplined curiosity is the exact right posture to have. Quantum computing is way too significant to ignore, but the hardware is simply not mature enough yet for you to blindly believe every vendor claim without rigorously evaluating their noise levels and workflow integrations. Learn the mechanics, respect the limits, and prepare your defenses where it matters most. I want to leave you with a provocative question to take straight back to your teams. Look at your own organizational roadmap and ask yourselves, what would we do differently next quarter if we took quantum seriously but absolutely refused to be driven by hype? Really think about your long-lived data, your encryption standards, and your genuinely complex computing bottlenecks. Until next time, keep exploring, stay curious, and keep learning.